I am Paul Shepson, and I'm a student of bee ecology and dean of SoMAS. And I'm so excited to see you. Welcome to SoMAS. I can tell you're smart. We'll be seeing you here in the fall. Congratulations on that. So it's my distinct honor and a lot of fun for me to introduce our visitor and speaker today, Professor Jose Fuentes from Penn State. Jose grew up in El Salvador. He told me last night he walked something like 4 miles each way to school. I think it was uphill both ways, not in the snow. And then at some point he moved to the United States, to DC, and did a degree at Millersville University in Pennsylvania in bachelor's degree in dynamic meteorology. He then moved to Canada right around the time I moved to Canada many years ago. And he did a master's degree and a PhD degree at the University of Guelph with a fellow named Terry Gillespie, working on sort of boundary layer turbulence and turbulent transport of pollutants to the ground. So he studied dry deposition of ozone. Steve Schwartz is nodding with that. He then worked for Environment Canada, where we intersected quite a bit. And we both ended up heading north to the Arctic through Environment Canada years ago. So Jose's work that covers, he is like our faculty and our current students and all the new students, you will be very multidisciplinary. That's exciting because the Earth doesn't care what your discipline is. It mixes everything all together. And so it's your challenge to understand it all. So Jose has worked in boundary layer turbulence and turbulent transport of pollutants, boundary layer structure, sometimes focusing on boundary layers in stable environments, which is a big challenge for meteorologists. He's studied emission of biogenic volatile organic compounds, which we'll hear about today. Weird halogen chemistry in the Arctic. His science has taken him from the Amazon, spent a lot of time in the Amazon, various parts of the United States, parts of southern Ontario, the tip of Ellesmere Island at a place called Alert, where we spent some great informative time. And at Utqiagvik, which is the northernmost settlement on the planet at the sort of tip of the north slope of Alaska. So today, Professor Fuentes will, if I ever stop talking about him, I meant to mention, he's got 16,000 citations. He's a fellow of the American Meteorological Society, fellow of the AAAS, one of the two AAASs, and a fellow of the American Geophysical Union. So Jose's been around. So now I'm going to stop talking. He's going to talk about the Earth's beeswax or something like that.
Thank you, Paul, for that very nice and lengthy introduction. I'm very, very happy to be here. Thank you so very much. Also, the other reason why I'm very happy to be here is because I want to share with you some results on a research topic that is of great importance to me. This area does not necessarily represent the core research area that I do, but it really overlaps in so many ways. Paul mentioned something about turbulence. That's what I have done almost all my career. He also mentioned chemistry. So I've been really doing research at the interface of those fields. And as you can see from this cartoon that I have here together, the interactions between insects and plants is of great importance, not only from the point of view of ecology, but also from the point of view of the services that these elements of ecosystems provide to us humans. And I will make that point. So I'm going to give you a synopsis on basically what the principal reaction pathways are for these molecules that the flowers produce. And then I will share some results as to how levels of air pollutants that we traditionally see during the summer months can actually modify the scents that flowers actually release to advertise to the insect pollinators that can come to visit with them. And then I'm going to end up here with these ideas related to the emerging phenological asynchronies that are happening between the foraging patterns of insects and the emissions of scents. And those asynchronies are actually being driven by atmospheric warming on the planet Earth. Many perhaps in the audience here today have learned that our insect pollinators are in trouble almost everywhere in the world. Here in the United States, we have actually the statistics to show that at least the number of honey producing bee colonies have been increasing or decreasing rather, for a long, long time. And there are many hypotheses to explain why these declines are happening, and I will share some of those ideas with you in a moment. But this is one iconic figure that I like to cite that just to tell that our insect pollinators are actually in trouble. And not only that, but also we have other insects that are basically on the danger of disappearing. Of course, the iconic honeybee is basically experiencing some environmental challenges almost everywhere upon Earth. These beautiful bees here, the bumblebees, believe it or not, they are in trouble. There are some regions in the world where the bumblebees are almost at the brink of extinction. And these are some of the most beautiful bees, in my opinion, because some of them actually come wearing different jerseys. And there is one, the one that is in more serious trouble is the one that wears the Brazilian jersey, you know, the soccer jersey. That's the one that is in trouble. And then you probably have heard that for many years we have been destroying the habitats of the beautiful monarch butterflies. So we have a lot of work to do, and the solitary bees are also in trouble. And now, the fundamental reason that we should actually care about the health of our insect pollinators is that they actually provide some important services to us. On this diagram, what I would like you to pay attention to is that the pollinators actually have global importance, but also local or regional importance. And these are the dominant pollinators that we have, the bees, you can see, read the names in there. And on this cartoon right there, you can basically see what the fraction of their activity is in terms of pollinating ecosystems around the world. And in our case here in the United States, we see that the honeybees are the ones that dominate the pollination, and also that they play basically a global importance in that process of pollinating the flowers. And if you actually take all of the work that these pollinators do at the global scale, they actually contribute to food production in the order of $577 billion per year. That's a staggering amount of money that these pollinators actually are producing. And as it mentioned earlier, there are many, many reasons why our pollinators are actually in trouble. So one of them is that we humans are reducing their native habitats. We have been basically mostly destroying the habitat. In some regions, habitat fragmentation is a major, major problem, and therefore the insects or the pollinators do not have the necessary range to do their foraging. And then more importantly, this is the most pernicious impact on the bees. That we are releasing these neonicotinoids that basically are killing our pollinators. And I need to kind of parenthetically mention to you here that scientists around the world have been studying these issues here for a long, long time. And there are now countries that are banning the neonicotinoids simply because they are destroying the communities of pollinators. Two example of countries that actually have taken measures to do that are Canada and the Netherlands. And so, of course, we have diseases, and I will amplify this idea on the atmospheric warming. But one key stress that we haven't learned much about is this stress that actually that air pollutants impose on the pollinators. It's not a direct abiotic stress, but it is an indirect effect because we are, in a way, but when we introduce these air pollutants, reducing these signals that the pollinators need in order to locate the flowers. And so these flowers produce thousands of these molecules. Roughly speaking, about 2,500 different molecules are produced by flowers. And these flowers produce these very expensive molecules. For example, the petunia flowers that perhaps some of us here will grow during the spring, you have molecules such as benzaldehyde, which is a fatty acid derivative, limonene, which is monoterpene. These are really very expensive molecules for flowers to biosynthesize. And then for the sunflowers, you have the methylbutanol here, and then the myrcene, which are monoterpene. And the canola flowers, we have farnesene, which is a sesquiterpene right there, and linalool. If you look closely, one common feature on all of these molecules is that there is a double bond. And in organic chemistry, we often say, oh, yes, those are the molecules that will become very reactive with the atmospheric oxidants. So that's what we have. In addition, there are some flowers that are what we call deceitful flowers. They are deceitful flowers because they release these very nasty gases here like methyl trisulfide, and then they invite the insects to visit with them, but the flowers do not give any rewards to the flowers. And so these are the compounds that actually smell like decaying meat right there. And in the case of the squash flower, they produce these molecules that have nitrogen in them. And so these are very expensive molecules, very unique molecules, and I will tell you more about this molecule in the future. So even though these flowers produce large number of molecules, they only reside, the molecules, in the environment in trace levels. Yet the pollinators have been trained to detect very, very small trace amounts of these compounds. And yet, as I mentioned a moment, these are the most reactive molecules that we find in the biosphere. And so they really don't last for too long. But more importantly, these molecules really play a very fundamental role in the area of pollination. And so most bees actually are expected to see a bouquet of emissions. So when, for example, a bee is foraging in the environment, it will actually do a transect like the bee that you see there on the screen. And that bee is going to be detecting these little spikes, which in organic chemistry, we call them the chromatograph. And every little peak that you see there represents an individual molecule. It's very rare for bees to detect individual molecules unless the bee or the insect is a specialist. Most pollinators are generalists, meaning that they actually detect this array of molecules that belong to these families of gases, such as the monoterpenes, the aliphatic acids, the terpenoid alcohols, and the aromatic alcohols there. So this is basically what they do, the pollinators, and that's basically what I have been studying. The other very interesting feature of these interactions is that as we have in the field of actually ecology and biometeorology, we have learned that the emissions of this sense actually is a function of the temperature. So the maximum emissions that we see is actually coinciding when we have the maximum temperature in the environment. But interesting is when the pollinators are visiting the flowers, like this flower you see here, this is the pussy willow flower that actually is very abundantly produced in the eastern part of the United States. Then the bees synchronize the visitation of the flowers to coincide when we have the maximum rates of emissions right there. And so one of the hypotheses that I have been working on is whether these scents are more rapidly destroyed simply because the maximum emissions, the maximum bee visitation of the flowers happen when we have the greater levels of ambient pollutants as represented here by the ozone levels in the air. So the ozone levels change from 0 to 120 parts per billion. This, I just randomly pulled this data from the EPA site. And what you see in this line here, that is the Environmental Protection Agency 8-hour average ozone national ambient air quality standard, which right now is set at 70 parts per billion. But if you look, even for us, ozone is not healthy. And so I'm also going to share the evidence with you that ozone is not even healthy for the bees either. So this is something that we need to work, and this is something that can benefit not only the pollinators, but also our human health. With that lengthy introduction, I'm going to now share with you that the next slides are going to address these research questions that I have here. I'm going to share the results that under the current levels of ambient air pollutants in places such as the Eastern United States, those pollutants actually modify the integrity of that bouquet that I mentioned a moment ago. Also, the strength of that signal that the bees or the flowers produce for the bees is going to change because of the chemical reactions. And so in environments such as the one where we are here today or close to New York City, we have lots of nitrogen oxides around the air. That happens simply because, you know, if I was parked here on the highway yesterday on my way out here, there are lots and lots of vehicles around that are basically burning things. And whenever biomass is burned or even fossil fuels, then there is the generation of a molecule that we call the nitric oxide. So when we have those compounds in the air, these molecules undergo what we call ozonosis. And therefore, we're going to see that these molecules will be destroyed, the scent molecules. And then ultimately, of course, what we want to know is how those changes in the fluorescence will impact the foraging patterns of the bees, that the bees basically follow the plume of the scents that the flowers produce. They follow the gradient actually. But if we have air pollution, then those pollutants can in fact reduce the emissions if the pollutants are in high concentrations. And therefore, it is quite possible that the discovery time that the bees would have to locate the flowers may be modified by the chemistry. So when I talk about oxidants in the atmosphere, I simply refer to the levels of ozone, the hydroxyl radical. During the nighttime, we have plenty of nitrate radicals in the environment. And so all these molecules that you see here, such as beta-osamine, beta-marcina, linalool, will react with these molecules you see there. And then, as I'm showing in this cartoon here, those reactions will lead to the formation of new chemical species. Some of them are like acetone, formaldehyde. Formaldehyde is a very intriguing molecule because it can undergo photolysis and also give you more hydroxyl radical that will feed back to exaggerate or enhance the chemistry. So one of the ideas that we are still exploring in my laboratory is whether these reaction products that you see here are being detected by the bees, whether the bees are evolving to detect these reaction products right there. And as I said, these reactions are principally happening with these three oxidants. And in the next results I'm going to share with you, I'm going to focus mostly on the reactions involving ozone, the hydroxyl radical, and you can see here, these are the rate reaction coefficients that for the ozone are in the order of 10 to the minus 16 centimeters per molecule per second, whereas in the hydroxyl radical is in the order of 10 to the minus 10, the units that I just mentioned a moment ago. And so I'm going to share results that I have generated with a very simple Lagrangian model that I have produced. In that Lagrangian model, I calculate the turbulent transport of these gases emitted by the bouquet of flowers. And in addition, as these air parcels are moving across the landscape, I am basically doing the reactions of those molecules. And I have developed some chemical mechanisms. These reactions that you see here, well, these are actually, these are only for the DN to see, not for the rest of you, just to see whether the DN can follow the chemistry here. So here, they have the ozone basically being photolyzed, and that would produce the hydroxyl radical there. This is what I call the inorganic component of the photochemical mechanism that we put together. And then I am dealing with a bouquet of flowers of the canola plants. I'm basically choosing a plant or a plant canopy 1.2 meters tall, leaf area index of 2, and then I calculate the emissions, turbulent transport, and chemistry, and then I use the turbulence levels of about 0.25 in the form of the friction velocity. And then these emissions are happening continuously, and here is actually the condensed chemical mechanism, in this case, for the molecule that I'm going to, that is called the marcin. And that, in this case, in this mechanism, I'm allowing the reaction of the marcin with the ozone that produces this, we call this the Krivy radical, and then you see the acetone molecule again being produced. This free radical then will combine with hydroxyl radical, which in the presence of the nitric oxide will generate the nitrogen dioxide. And down below here, you see the formation of the hydroxyl radical. So this is what I was indicating earlier, that the ozonolysis actually will produce this hydroxyl radical. And in the case of the reaction with the hydroxyl radical, we will end up basically to follow the reaction pathway to actually observe the formation of the formaldehyde molecule. It doesn't really matter what you see in the reaction products. The reaction products don't even look closer to the parent molecule that the flowers are actually producing. At the end of my talk, I'm going to actually invoke the idea that our planet is actually warming quite rapidly in these days. And I'm going to argue that these reactions that I just described to you are very sensitive to the temperature. Right here, this is the Arrhenius expression that tells me what the rate constant is for these reactions. And what you can see here, that we have the temperature. So if we see some changes in the temperature, we will impact the emissions, we will impact the reactions of all these molecules. I will come back to that idea. And then finally, I have a very brief description here of the Lagrangian model here, which I'm basically calculating the change in the velocity. This is the velocity vector here for the particle. I release particles from the crown of the forest. I can choose how many particles I can release. And as these particles are moving, these are air parcels, I do the chemistry of this compound. So I do here the velocity field using the A here, which I am, this is the drift term, and the B, that's the diffusion term. And those quantities basically depend on the kinematic momentum fluxes. So, and then of course, the other variable that we need to work here is the so-called the dissipation rate of turbulence, which I define in terms of the friction velocity. And then basically this tells me the ensemble size of the eddies in the domain that I'm choosing here. So that's basically what I do with the numeric model. It's a very simple model. I have worked with all the models, but my colleagues in the field of ecology, they often say, we cannot run your large eddy simulations, but when I give these models to them, they can do all the calculations, and then we can actually make progress with the science that they want to do. So first of all, just to repeat, I'm going to do the chemistry for the bouquet of scents released by the canola flowers. Here are the agronomic practices that I implemented in the model. On the bottom part here, you see the chemical species that are released by the canola flowers. You have sesquiterpenes, monoterpenes in here. And so these are the emission rates that I calculate at the landscape level here. So there's a really, you can see here that these are basically small emission rates. And then on the middle graph, I have basically the concentration of all those scents, and the concentrations are molecules per cubic centimeters, and then expressed 10 to the 9. So these are really very trace amounts. This is in the fraction of a parts per trillion in the mixed ratio. And then I calculated the hydroxyl reactivity, which I define as the concentration of the scents times by the reaction rate coefficient of the hydroxyl radical with that scent. And so this figure here tells you basically the scale as to how reactive these molecules are in the environment. And for here, I'm just giving you the average ensemble average for the bouquet of reactivity. And for reference, I'm giving you here the reactivity for isoprene, which is the most abundantly emitted molecule by the vegetation. And that's what you see in there. And then in terms of the lifetimes of these scents, you can see that the lifetimes with respect to the hydroxyl radical is just simply in the order of a few minutes for molecules such as farnesene, and then probably a fraction of an hour for the rest of the molecules. The lifetime with respect to ozone for the levels that you see here, basically they are in the order of hours. So these molecules cannot be expected to travel long distances in environment where we might encounter the hydroxyl radical and the ozone levels shown in this diagram right here. And here are the results. Using the Lagrangian model, in this case, I simply want to illustrate that there is a variety of the dispersion, turbulent transport, and chemistry of these species. For example, in the case of the alpha pinene, that molecule can travel basically, probably 1,200, 1,500 meters. But when we have molecules that are reactive, such as the farnesene, they basically remain confined very close to where the molecules are released. And that happens simply because the reactions are really, really fast. That's basically what happens. And so when a bee is foraging throughout the landscape, that bee will be looking for plenty of farnesene, but most likely that bee is not going to find any farnesene close by the nests where the insects are housed. And then here's where I want to basically report to you how air pollutants can actually modify the informational signature that is conveyed to the insects in the form of the bouquet. First, I need to explain here that on this part of the slide, I have all the molecules that are released at the crown of the plant canopy, right here. The dominant species here is beta-marcin, and then we have the next one here, limonene, and that at the bottom here we have the molecule that we call farnesene. Now, on this side of the slide, I have three scenarios. Scenario 1, ozone 40 parts per billion, nitric oxide 0.25 parts per billion, nitrogen dioxide 1.5. These are the conditions that nowadays we experience in the rural atmosphere of the United States. On the other extreme here, I am giving you the conditions that tend to prevail mostly in and downwind in urban environments there. So if you look closely at this the molecule here, it's still present 100 meters downwind from the flowers, a little bit at the 1200 meters. But when I go to the polluted environment, there is only very little marcin in that environment. And if I go and look at the farnesene, farnesene is only found in the first 800 meters, and then it completely disappears in the polluted air mass that I have at the end. This is the evidence that I have to illustrate that in polluted air masses, the signature those bouquets of scents provide is really modified by these reactions that we have in there. And then the last question I want to share with you is that I go back to the ozonolysis of these molecules, and what I have done here is that I'm plotting the fraction of the fluorescence on the vertical axis and the downwind distance on the horizontal axis. The solid lines with the circles represents basically the changes of these scents without any ozonolysis. But when I add ozonolysis, you can see that there are some appreciable differences. And those differences actually depend or range from around 10 to 40% on a per molecular basis, depending on the scenarios of air pollutants that I am using. And so I am here sharing with you that in and around urban environments, the previous processes that I illustrated that can actually diminish the levels of these scents actually are exaggerated. They are enhanced in those environments. That's what we have. And so just to illustrate the point further, what I have done is that I have calculated the hydroxyl radical concentration for the marcin. I am basically changing the levels of the marcin. This is the one that I shared earlier, and that's basically the change in the yield of the hydroxyl radical as a function of the nitrogen oxides in the environment. This line that you see here on one and below, those are the nitrogen oxide levels that we typically observe in the rural atmosphere. But if you look at this diagram here from a textbook that Professor Tim Oak from the University of British Columbia published a few years ago, you can see that the levels of the nitrogen oxides here, this is the concentration, they actually go all the way up to 250, which is much higher than the national ambient air quality standard set by the EPA. Similarly, for ozone, you can see how they change in downwind. So in and around cities, this process of having production of the hydroxyl radical from the essence molecule is actually providing a feedback mechanism that actually contributes to further reducing the levels of essence that the flowers produce. And so this is just kind of a summary to share with you that when we calculate the foraging times for the insects that actually are experiencing those changes in the plumes of scents, I have plotted here the scent detection threshold that the bees have. Bees, believe it or not, can only they can respond whenever 6 molecules are impinging on the antenna simultaneously. And that's where that threshold value comes in here. And you can clearly see that when we have no ozone in the environment, the foraging times, let's say when they have one, is probably around 10 minutes. But when we go in the polluted environment, that foraging time can go all the way up to 50 minutes. So there is a difference there of about 40 minutes. So this is exactly what is happening to our pollinators in environments where the air masses are polluted. And so here is an article actually that was inspired by my research that in which these investigators went out there to really interrogate the bees. Tell us how long you take to make the trip when you leave the hive and then come back. This is the pre-polluted here, and all those dots represents basically the sampling that they did for the bees. And then the pollution levels expressed in the particle concentration are these triangles that you see here. And you can clearly see that in the outdoors, the insects are exactly experiencing what I simulated with my numerical model. So that is the evidence that we have that we are in a way confusing our pollinators in environments where we have plenty of pollution. Now, I have done field work too. I have gone with students to visit the bees and of course to kidnap them. And the way that we kidnap them, we use this device. And then once we capture the bees, we put them in these vials. And then we
that picture on the upper left, that must be a grad student, right?
actually no, this is a REU student. The research experience for undergraduate students. And I have to tell an anecdote just to follow up with what the dean is. When I recruit undergraduate students, they often say, you know, because we ask them who they would like to work on the faculty, can I please work with the bee man? That's me. So, and I don't have many positions. I have only one or two. And so what we did is we kidnapped the bees and then we induce siestas. So the bees have to have a little bit of siesta. And so once they have the reason for having the siesta is that we put these restraining harnesses on them. So that, and then after they wake up, we give them some food. And then the idea is that we want to know if the bees like polluted air or not. And in order to learn that, we do this test that we call the proboscis test. And if you want me to translate into English or Spanish, it's like asking the bee, can you please show me your tongue? So that's what it is, right there, right there. And so with Kim Aggie from San Antonio, Texas, we built these instruments right there. And then we had these probes right there where we actually were releasing the scents and the polluted air and asked the bees what they thought about the polluted air. And so, and then here's another set of experiments in which basically we put the flowers in a cuvette and then we ozonize the flowers. And then we use this ones here because the bees are not very collaborative. They are very, very hyper. And so we decided for one experiment to actually use the striped cucumber beetles because they are very collaborative. And so they were asked to decide whether they like polluted air. And then this is the diagram in here. This is where the reaction took place. We had enough residence time in this reaction chamber there to alter the emissions from this flower here. And the most important gases emitted by this flower were indole, formaldehyde, and the trimethoxybenzene. This is the very intriguing molecule I showed you earlier. And here are the results. And so in this diagram, what you see is the percentage of choices. Each experiment entailed 100 different insects. And so we have a lot of data in there. So when the ozone levels were 20 parts per billion, that's the mixing ratio, there was no preference for the bees to either choose the air coming from ozone and the flower or just the flower. But when we reach the level of 80 parts per billion, that's when the bees told us, or this insect, no, we don't like polluted air. Also, right there. So that's the experimental evidence that we have that air pollutants do indeed confuse our pollinators. And then I am still doing some ongoing studies One study that we are doing is that we want to learn how we can determine in situ the foraging patterns of insects. And the way that we're doing that is that first we are using this radar. This is a radar that perhaps your dean has on his boat or his yacht. And then we basically send a signal to this device, this instrument that we put on the bees. And then from that transponder, we collect the signal on the radar antenna, and then we process data and we display the information of the bee. So right there, anywhere this trace you see there, that's the trajectory that the bee actually has. And this is, Paul Shetzer may remember this because he went to Penn State for graduate studies. This is the agricultural experimental farm at Penn State. Here's where we have the radar, the transponder there. So we were testing this. This is a technology that we are actually producing. Right now, we can only do one bee at a time. And so we are now changing the technology to do multiple individuals simultaneously. So that's coming. So that's, I don't have the results to share with you. And I want to end today perhaps on a sad note. All of us in this room hopefully realize that our planet is actually changing very rapidly. The air temperature, as you can go all the way back to the 1880s to 2023. This is the departure of the temperature anomaly with respect to the climate norms 1551 and 1980. You can see that we have this trend in the temperature for both over land and also over the ocean. And what I want to call your attention to is that in the last 8 years, the warming actually has been unprecedented. And one feature of the climate that is happening is that the warming is not happening in a uniform manner. There are regions of the world where the warming is exaggerated. And so what I have done, I went to plot the temperature for the months of just May, for those years when we had the unusual warming. And you can see here that the most part of the western part of the country is basically experiencing warming that is more than 2 degrees than the normal. That's for the month of May, for those years. The same thing happened. More than half of the country was experiencing air temperatures that were exceeding 2 degrees above the norm there. And then finally, you have for the month of August, those are in my way of thinking, the months of the growing season. So you can see the places where the planet is actually disproportionately warming than the other places. So these changes in the Earth's climate, and you have seen these plots, with respect to the various scenarios that are projected for the next years. These projected climate scenarios are going to impact ecosystems in ways that we haven't really envisioned yet. In fact, if you look at this bar here, that it says the impact and risk assessments, assuming low but no adaptation, we already have that some ecosystems are at risk. And I will submit to you, because of the idea that I already shared with you, that these reactions happen more rapidly with higher temperatures. That will be one effect that will be exacerbated because of climate change. Additionally, we know that the biosynthesis of these molecules is actually following this line that you see here, this cartoon. That's what we know now. And so the system is working in synchrony right now. But when we now go to experience these very extreme features of the climate, we will experience that the emissions will happen much earlier because the flowering season is happening earlier, but the insects are expected to do some foraging in the way they have been doing this for forever. So this bee foraging will not be synchronized with the flora emissions due to those changes, just in the temperature field alone. In addition, if we invoke that in some regions, we will experience prolonged droughts. Those droughts will basically have abrupt emissions of these floral scents, and therefore these plants will not have the necessary mechanism to advertise to the pollinators that the resources, the floral resources are not there. And therefore the bees will be foraging, but without really harvesting the necessary food to sustain the future generations. And I gave you the evidence that the quality of the scents will change as well. I gave you the results here to say that the composition is changing because of the polluted levels, but also that these molecules will not travel the necessary distance that the insects can actually detect them. So the bouquet of scents from individual flowers can fail the specificity in terms of the informational composition that the flower mixtures provide to the insects. I know that this sounds probably on a very sad note, but I think the challenge for us as citizens of the planet is that we need to realize that climate is not just impacting us. Climate is also impacting ecosystems and the elements of those ecosystems. We depend on those ecosystems. If you ask me, I mostly eat vegetables. If I cannot have my zucchinis, I will be in trouble. So I want to have my zucchinis, for me and hopefully for my future generations. And I think we all need to do the best we can to really tackle the source of these problems. I was speaking with the dean earlier, we have documented evidence that if we concerned citizens really tackle environmental problems with the seriousness that they deserve, we can actually succeed. And an example that I like to share with my students at Penn State is that in the 1970s and 1980s, we had a major problem with acid rain in the eastern part of the country. Most of our lakes lost their aquatic life because of the acid rain. But then in the 1980s, Congress, the US Congress, scientists, concerned citizens, and even industry got together and said, we will eliminate acid rain. I bet you that the new students who are here, I visited for graduate school, probably don't hear much about acid rain. And that is because we solved the problem. We can actually work in the same way with this one. And so I want to leave you with these conclusions here about my studies, that even in the most moderate polluted air masses, these floral scents, they only travel short distances, not the necessary distances that the pollinators need to locate flowers. And in addition, that the scents may also impact the local oxidation capacity of the atmosphere through the process of ozonolysis. This is a very new idea. I still haven't published that. And I already gave you plenty of evidence to suggest that air pollutants do modify both the quantity and the quality of floral scents, and also that the ability of the bees to discover the scent plumes basically is impacting the foraging patterns, and that will impact, of course, the crops upon which we actually depend. And so this is the message that I want to share and leave you with, that the emerging evidence indicates that the degradation of informational factor signals provided by the floral scents as they react with oxidants. And there will be this phenological asynchronies of the scent emissions and the foraging patterns of the insects. So I think, yes, the conclusions sound very sad to some extent, but the message that I will leave you with is that we all need to work together to solve this problem. And I thank you very much for your attention.
Questions?
Yeah, thank you very much. Great job. I want to go back to a dispersion model. You did hold the nitrogen oxide constant. What was the rationale and what implications did it have on the dispersion of the set?
So in this case, the nitric oxide, nitrogen dioxide, and ozone, that they remain constant throughout the model domain. The only variation that we allow is to have a profile of those gases with altitude. So there was a little variation of these gases with altitude, but throughout the domain, they remain invariant. And so when you are dealing with relatively small domains, 2,000 meters, really very small domains, you can get away with that. But if you were to have a domain going from here to Chicago, yes, we need to include the spatial variability of these reactants in the model domain. So that was the rationale.
Thank you also for a great talk. So I can follow your argument about deep foraging phenology not responding to change in conditions. And with lots of other populations, see the phenology change with climate change.
But the
ocean temperature. So,
but the evidence that we have so far is that the emissions of the fluorescents are happening sooner. And so in other words, like in Pennsylvania, for example, I work with colleagues who are trying to determine the scent emissions from the apple orchards. You know, we get sometimes that the emissions happen in late March, early April, but the bees come much later. They are not out yet. And so they miss the peak of the blooming right there. And so that's what I am referring to, the asynchrony in there. Perhaps that's just an anecdotal evidence, but I think we have evidence for other scientists who are working in other systems that they see that the maximum emissions are not happening for some flowering plants at the same time when the insects are coming out. And I need to add, I think this is a very important point that perhaps you're making, that those asynchronies are more conspicuous in temperate environments. In the tropics, I don't think that that would be a major issue. Yeah.
Hi, thanks for a great talk. I really got why you use the National Ambient Air Quality Standard on that graph. And what I know about that is that, you know, those decisions are made based on human welfare and ecological welfare decisions. That's how they're set. And, you know, full stop, that's about all I know. But how does this work feed back into sort of institutional decision-making about those types of standards?
Well, let me say, as one of the members of the advisory committee who was working on the national ambient air quality standards, we have very limited data, to be honest with you, about the impacts of pollutants on human health. But what we have done actually is to really get data on how air pollutants impacts ecosystems. For example, in the case of ozone, the national ambient air quality standard was set in response to having plants that exhibit some stresses because of the excessive assimilation of ozone. So in terms of setting up, you know, the standards, I would say to you, yes, let's work with that. I mean, in the standards, the way we set them out, we have the primary standards and the secondary standards. The primary standards are supposed to protect human health. Secondary standards are supposed to protect private property, as per the Clean Air Act. But for ecosystems that are very sensitive to this, what I would say is, why don't we all work in terms of having a cleaner environment? Regardless, whether the private property or whatever you want to include in there is adequate. I would go and say, well, historically, these ecosystems were exposed to these levels, and we have evidence as to what those levels were. I think that should be the goal that we should be striving for, because we need to minimize the impacts of our activities on these ecosystems. Yeah, and the other point to argue here is that what you're going to have if you go from the gradient that Shepson mentioned earlier, from the rainforest, the equator, all the way to the North Pole, you're going to have various degrees of sensitivities to those systems. So I would argue, let's not disturb the environment to the extent that those changes will be detrimental to ecosystems or elements of ecosystems.
I think we have time for one last question. John, do you have your?
Oh, just nails. Okay.
No, you asked me the side, I think. One last.
Hey, Jose, great talk. What are they honing in on? Do we know? Because you said they're generalists, but they're not picking up things like alpine, the bees, right?
Yeah.
So do we know what they're detecting, what groups they're detecting? Because alpha pining's got a ring, and like a lot of the other, I couldn't read all of your terpenoids, but a lot of them had, rings, but it's not that. Because alpha beta pinene are super common. So do we know what they're detecting?
And yes, I think we have very well developed field. My collaborators actually, they use an instrument which is called electroantennogram. And actually that's how they get the threshold detection of each molecule on the beads. One of my collaborators from the University of Virginia, Tyler Ralston, he uses that instrument to really see, number one, the detection level or the threshold level, and then he cranks up, the different bouquets that he asks the bees to recognize. And that's how we now know that the bees, by and large, only detect mixtures, not an individual molecule.
So it's like a matrix.
Yeah, it's mixtures. Yeah, and so they are trained to detect, fractions of the mixtures. Yeah, yeah.
Okay, thank you so much for this.